Good afternoon. My name is Fabio Gonzalez, and I'll be presenting the Chapter 18 overview alongside my partner Donovan. So first, we're going to start with unit cell dimensions and the radii of particles. So we're going to relate them to each other. So first, we're going to start with the simple cubic unit cell. This unit cell it consists of 8 corner atoms. So we have 4 at the top and 4 at the bottom, as seen in the diagram below. And then each corner represents 1/8 of an atom, since it's just a corner atom. And so that means that we have a 1 corner atom per unit cell. And also, as you can see in the diagram, the corner atoms touch each other. So therefore, one side length is going to be equal to two radii. So equal to 2 radii of the particles making it up. And moving on to FCC unit cells, they're going to have the 8 corner atoms. So that's going to make up 1 atom. And then they also have a face atom on each side. So these make up half of an atom, and since there's 6 of them, that's going to give us 3 face atoms. So if we add the 3 face atoms and the corner atom, we have a total of 4 atoms per unit cell for the FCC unit cell. Relating this to the radii of the particles, we see that in one face diagonal, we have 2 corner atoms. So that's going to mean we have 2 radius, 1 radius for each one. And then the face atom is gonna have 2 radii, since we're given the diameter of the whole atom. So therefore, one face diagonal is gonna be made up of 4 atomic radii. We can also apply the Pythagorean theorem, where 4 radii squared equals length squared plus length squared, since each side is gonna represent length of one face. And so when isolating the r and making it in terms of length, we get 0.3536 length. Moving on to the BCC unit cell, we see that it has 1/8 of corner atom in each corner, like the other unit cells. So there we have 1 corner atom, and then also has 1 center atom in the middle. So it's going to have 2 atoms in total, since it's not sharing the center atom. And then in terms of the dimensions and radii, we can see that there's a body diagonal that goes from the bottom left corner atom to the top right corner atom. And although the corners don't touch, the corner atoms do touch with the middle center atom. So therefore, we're going to have 4 radii, since we have the radii of the left bottom corner atom cell, the radii of the right top corner cell, and we have 2 radii representing the diameter of the center atom. So like the FCC unit cell, we're going to have 4r for the hypotenuse. However, when we set the radius in terms of L and use the Pythagorean theorem, it's going to look a little different, since we're going to have 4r squared for the hypotenuse equals L squared for one of the lengths, and then the square root of 2 lengths squared. And then when we solve this out, it's going to give us 0.4330 length for the radius in terms of length. So let's go ahead and move on to relating the densities of solids to unit cell dimensions and the mass of particles. So this is quite simple. So let's say we have this molecule, and we know that the structure of the unit cells is FCC, so face-centered cubic. So first, we're going to have to go ahead and solve for the mass, since density equals mass over volume. So to solve for the mass, first you have to see how many atoms you have in your structure. So we know that an FCC unit cell has a total of 4 atoms due to the corner atom, one corner atom, and 3 total face atoms. So this means that first we're going to go ahead and convert it to moles. So to convert it to moles, we're going to have 4 atoms of the molecule times 1 mole of the molecule all over 6.022 times 10 to the 23 atoms of the molecule. So this is Avogadro's constant, and this is going to give us the units of mole. Afterwards, we're going to multiply by the molar mass of the molecule. Let's go ahead and think of a solid. So let's say we have a solid ferrite. We'd use its molar mass of 55.845 grams all over 1 mole in order to convert to grams and get the mass. So then once you have the mass, you can move on to finding the volume. So to find the volume, we know that these cells, the FCC, BCC, and simple cubic, are all cubes. So the volume is going to be the length cubed. So once you know the the length, you simply cube it, and if let's say if it's in units of pm, then you simply convert to centimeters. Then once you have that, you simply use the density equation of mass over volume, and you get the density of the solid. And now let's discuss the difference between substitutional and interstitial alloys and how to distinguish between both of them. So starting with substitutional alloys, those are metals where some of the host atoms are replaced by minor elements. And this adds strength to the alloy by adding roughness to the material. And what it means by roughness is that usually the metal atoms, or the atoms inside the metal, they can slide past one another. But when you add atoms of another element of, let's say, bigger size, it's harder for the atoms to slide past one another since they're different sizes. Some examples of some substitutional alloys would be like bronze, in which there's some tin atoms that replace some of the host copper atoms. Another example would be brass, where zinc replaces some of the copper host atoms. So moving on to interstitial alloys, these are different because instead of having the added element replacing some of the host atoms, you have the added element residing in between the holes between the host atoms. Because remember that the atoms are circular, so there's going to be space in between them. And this is where the added element resides, so it's not replacing any of the host atoms. And there's two different sized holes, and there's different sized holes, and there's two main hole sizes in the closest packed crystal lattices. With the first type of hole being the octahedral holes, which are larger and are surrounded by 6 host atoms, and then you also have tetrahedral holes, which are smaller and are surrounded by 4 host atoms. So the elements that occupy these holes, it all depends on the size of the elements. Since if they're too big, well then they won't fit in the tetrahedral, might fit in the octahedral. And then this also prevents host atom slippage, that strengthens the metal. And some examples would be carbon steel and iron carbide. And iron carbide, you have carbon lying in between the holes of the iron. So in summary, to distinguish between substitutional and interstitial, you have to determine whether the added minor element is either replacing the host atoms or a line between the spaces created by the host atoms. So now let's move on to discuss how band theory explains the conductivity of metals and semiconductors. So band theory describes how when atoms overlap, or when atoms bond together, their orbitals overlap, which we already know this from the chapter of molecular orbitals. So when we're talking about solids, like metal solids, we have so many atoms overlapping since the solids are so dense that the molecular orbitals overlap to such a degree that the lower energy orbitals and the upper energy orbitals actually are connected through an overlap of bands. Since the bands are so continuous that it actually connects both of the bands, or both of the upper and higher level orbitals. So then this allows for the movement of electrons between the upper level of orbitals that are empty, and the lower level, which are filled or partly filled. And these represent the two bands, with the partly filled lower energy orbitals representing the valence band, and the non-filled the conduction band. And so let's say we have an example where we have a metal that actually fills up all its orbitals. Well, let's say it fills up all its 4s orbitals. Then we still have the p orbitals that overlap that are empty, and that still serves as a conduction band where electrons can move up. And since there's so many of them, so many atoms that are overlapping, the p orbitals are actually going to be really close to the s orbitals, and there's still going to be electron movement. And so because electrons can move between the bands, we're going to have there's going to be good conductivity of electricity. A similar idea applies to semiconductors, except that with semiconductors, the bands don't overlap. Instead, there's a small energy gap. This means that only some electrons can move back and forth between the two bands, since they have to be high enough in energy to cross that gap. This describes why semiconductors aren't as good at conducting electricity as some conductors. And although there's 2 types of semiconductors which can enhance the conductive abilities of the semiconductor, with the first being n-type conductors. In n-type semiconductors, some of the host elements are replaced with atoms of another element that possesses more electrons. By providing more electrons to the material, there's going to be more electrons that can move between the conduction and valence band, and therefore the conductivity of electricity will increase. A second type of semiconductor is a p-type semiconductor, where again we're replacing some of the host atoms with atoms of another element, but in this case the atoms of the other element will actually possess less electrons. This creates an acceptor level where there's going to be a positive charge, and as electrons move between the bands, there's going to be positively charged holes are created. They're going to attract the electrons from returning, and this promotes electron movement and therefore conducts more electricity. There are also materials called insulators that prevent electrical flow, so they're not good electrical conductors. And band theory also explains this, because band theory describes that in insulators there's a really big energy gap between the conduction and valence band, so electrons won't be able to move between both gaps easily.
Now we will discuss crystalline solids, including ionic solids, molecular solids, network covalent solids, and also ceramics. So first off, what differentiates these crystalline solids is the forces that hold them together. Ionic solids are held together by ionic bonds. They are composed of lattices of oppositely charged ions. For sodium chloride, sodium is positive and chlorine is negative, and the electrostatic attraction between them is what holds the solid together. Ionic solids are usually strong but brittle and have high melting points. Molecular solids are held together by a group of forces called the van der Waals forces. These forces include dipole-dipole interactions, hydrogen bonding, and London dispersion forces. They are often soft and have low melting points. Next is covalent network solids, which are held together by covalent bonds. They consist of chains of atoms or molecules, and this chain can be extended into a continuous network. They are usually hard with high melting points and are non-conducting. Now on to ceramics. Ceramics are non-metallic crystalline structures that usually contain oxygen, nitrogen, or carbon. Ceramic materials are brittle, hard, strong in compression, weak in shearing and tension. They are also electrical and thermal insulators. That will sum up crystalline solids. Finally, we will be discussing Bragg's equation and diffraction. So first, let's talk about waves. Unlike matter, waves can overlap and occupy the same region of space. When waves combine, they exhibit superposition. There are two types of interference that occur when waves interact: constructive and destructive. In constructive, waves that are exactly aligned and form a resulting wave with greater amplitude. In destructive interference, waves can cancel each other out and result in zero amplitude. This behavior can also be used in X-ray diffraction. When waves enter a small opening, they will bend around the corners. This is known as diffraction. In X-ray diffraction, X-rays are directed at a crystal and collide with atoms and scatter. The angles at which X-rays are directed at the crystal can affect the intensity of the resulting scattering waves. We can then use diffraction angles and Bragg's equation to find the distance between different planes. Where lambda is the wavelength of the X-ray, d is the spacing of the crystal layers, theta is the incidence angle, or the angle between incident ray and the scatter plane, and n is an integer. Then, by using Miller indices for values for h, k, and l, and the equation for unit cell size, we can solve for the values of a, b, and c, which tell us the edge lengths of the unit cell. That will conclude our Chapter 18 overview. Thank you for listening.